All right, we're going to be talking about the logistic model because a lot of exponential growth, populations grow exponentially a lot of times. Diseases spread exponentially a lot of times. But the problem with that is that if we have an exponential population model, eventually we're going to say that there's going to be 50 quadrillion people on the planet because exponential growth works like that. It just gets really, really big, which is ridiculous though, because the planet cannot house that many people, right? Ecosystems cannot house more than a certain number of animals. And if you have too many, maybe there's not enough food to sustain them. Maybe there's too many predators picking them off and they can't grow past a certain number. So there's some idea of carrying capacity for a lot of applications. So what we're going to do is introduce a model that includes the idea of a carrying capacity. So here is what we have. N of t is equal to c divided by 1 plus a e to the negative b times t. There's a lot of variation in how this model is named, but this is essentially what we've got right here. And this models exponential growth with something we're going to call carrying capacity A. So not A. Carrying capacity is C. I renamed these. Okay, so that numerator, that is our carrying capacity, okay? And we haven't mentioned exactly what that's going to be. All right. So it's great to use this for applications of exponential like population models inside some sort of ecosystem, and also for the spread and transmission of diseases. And you'll see why when we look at a graph of one of these. Okay, so I'm going to give you a graph of y is equal to 23082 divided by 1 plus 23081 e raised to the negative 0.05 times t. Okay. So, my numerator is flipped. There we go. You can see we have a y-intercept of 1. And specifically, let's change the domain and range. Let's look at a different thing. Let's go, time is going between 0 and, that, and the y-axis is going to go between 0 and, let's say, 25,000. So, look at this function. We wrote it as t, because t in this case is going to be days. Okay, so look at how we're going. We have about a year shown. We go up to 365 over here. Okay, so it started at 1. Our y-intercept was 1. It doesn't show it. We started with 1, and then it grew really slowly for a while, and then it gets really big really fast, and then it gets really close to this. And again, even if we change the domain, let's say 2 years is 730 or something, about 2 years, right? It's never going to get bigger than that 23082. That's what carrying capacity is, right? We're never going to get bigger than that number. It's an asymptote, a horizontal asymptote is what that carrying capacity is. Okay, so let's go back to 365. This is the spread, a model for the spread of disease. How many people total have contracted a disease? And so our carrying capacity right here, 23,000, that is the most recent estimate for the population of Rock Springs. Okay. And what was our y-intercept? Our y-intercept was 1. So assuming, there's a lot of assumptions in a model like this. This is one potential model that could be shown for if one person got COVID in Rock Springs and they spread it very slowly, right? If there's only one person that has it, it's not going to spread very quickly. But eventually enough people have it that it spreads very, very, very fast. Somewhere in the middle is the time where it's spreading the fastest. This is not an actual model for Rock Springs, but it could explain it. And then eventually, so many people have gotten sick that it lowers out. And again, it doesn't perfectly apply to COVID because there are documented cases of people getting the disease. It can, it can mutate and stuff like that. So it's not a perfect model. And again, I'm no infectious disease specialist, but this is just something that people can use for this. And there's a lot of papers out there, a lot of published papers very recently that model exponential or model the spread of COVID specifically and with this logistic growth model. There's a lot of really good ones for modeling the spread of disease in China, where this originated, and stuff like that. Okay, so that's sort of how logistic growth models work, and one way that they can apply to the spread of disease. So we're going to start this video with an example, specifically example number 4. Right? That's going to say a model for cumulative cases of COVID-19 in Wyoming is N of t is equal to 578,759 divided by 1 plus 250 e to the negative 0.02t. Here's one model for the spread of COVID in Wyoming, where t is the number of days after August 2nd, 2020. Okay, so what we've got right here, this is a model I made. I went to the Wyoming Department of Health website, and I actually came up with this model earlier today. Okay, and it's a pretty decent model so far, although we're currently more steep in real life than we are according to the model, which is a bad thing, but that's sort of what we've got over here. Okay, so I'm going to ask you some questions about this model as well. And again, look at the numerator. Numerator is the carrying capacity. Okay, what is carrying capacity? Carrying capacity is how many people could theoretically get it in the long run. So for a model in Wyoming, this is the most recent, the population of Wyoming that I Googled, 578,759 people. Okay. So we're going to ask some questions about this and use this model. Part A, going to be approximately how many confirmed, documented, however you want to say it. There's a lot to be said about that, but we're not going to say it here. How many confirmed cases are there on November 3rd? And November 3rd, that's going to be 93 days after August 2nd. So November 3rd, as of the day that I'm recording this video, is the most recent full day that we have documentation for. I'm recording this on the 4th. Right? So we are going to be able to use this function to model it. And hopefully, if I created a good model for this with logistic growth, hopefully the actual number should be very close to what we projected over here in this model. Okay, so we plug in 93 for t. 93 days. So n of 93 is going to equal 578,759 divided by 1 plus 250 e to the negative 0.02 times t, which is 93. And again, you just type this into a calculator. Don't try to simplify things one at a time. Just type the whole thing into the calculator. We're dealing with people. We're going to round to the nearest whole number. Okay, so if you type this into a calculator, 578,759 divided by parentheses 1 plus 250 times e raised to the negative 0.02 times 93, you're going to get approximately 14,499 people in the state of Wyoming currently have or have had, so this is cumulative cases, number of people who either have it now or got it already is 14,499 people. All right. And the actual number, according to the website I used, is going to be actually 12,399. Okay. So again, I said it's not a perfect model. It's ballpark. Actually, I think I did something weird because it was supposed to be closer. But then our actual curve is more steep right now than this is. Okay, so that's how you use the model. You just plug in how many days have passed, plug it in, type it into a calculator, and see what you've got. Okay, I'm a little curious about that, but I don't have time to check about why that's a different number than I expected. Okay, so going to be part B. Part B is going to be if nothing changes, right? So this means, if there's no, if there's no state shutdown, if people don't social distance, if people are, going at a large gathering, throwing giant parties and all this stuff, which is a potential over the holidays. So if nothing happens, like if this trend continues and we don't do anything, nothing changes, estimate how many documented, confirmed cases, however you want to phrase it, will have cumulatively. So again, not necessarily active cases and people who have already recovered. How many people will have gotten COVID on January 25th? Right. As a side note, January 25th is going to be T is 176. And this is a date of interest because you may or may not know, literally today, as of the recording of this video, you're watching this in the future, is the first day that the college has gone fully online because of health concerns. Okay. January 25th is the start of our spring semester. Okay. So ideally, hopefully, everyone can be smart, we can be safe, and we can slow the spread of COVID as much as possible. Maybe we're going to be able to have in-person classes. If things get bad, we're going to be online exclusively in the spring. Okay, so we're going to just plug in 176 into our model again. So you just do the exact same thing, but now we're plugging T is equal to 176. You type that into a calculator as well. What you're going to get, November 3rd, 12,000 cases. Well, we estimated 14,000, but it's 12,000 in actuality. If nothing changes and we follow this model, on January 25th, we're going to have 68,901 total cases. Okay. In about 2.5 months afterwards, the total cases will have almost been multiplied by 6. So that means in 2.5 months, there's going to be like 50-something thousand extra cases across the state if it follows this model, and if nothing changes. Okay, I'm optimistic that once we start seeing the rise, that hopefully people will do their part. All right. But anyway, so that would be bad. If nothing changes, this is a very bad number if it follows the logistic growth model, which again, there are documented cases of this following the logistic growth model. There's a lot of papers out there. There's tons of resources I can point you to if you're curious about this. So yeah, this is not good, but that's only a potential outcome. Let's look at this function, okay? Let's graph this and see what happens. So our carrying capacity, that's our numerator, is the population of Wyoming, 578,759. All right, our C value is 250, which corresponds to how many people had over there. And our coefficient is negative 0.02 here. Let's look over, let's say 90 days or something. Now let's look at, let's look at 90 days. See what happens over here. And we can see 3 months. Okay, in 3 months, this is what's going on. Let's go for a year, actually. 365 days. Oh, 365 days can have a lot more people. change the y coordinate to go up to 500,000. Again, there's about 578,000 people in Wyoming. So if nothing changes, this is the trajectory for how many infections, cumulative infections, we're going to have in Wyoming. All right. And again, I think things will change. I think they have to change. But it's crazy. Okay. And one of the issues with COVID in Wyoming is that for so long, we have so few people that for so long, it wasn't really an issue. Look at all these points down here, right? There's few enough people that it doesn't matter if we social distance. It doesn't matter if we go out because almost nobody has it. But at a certain point, there is a critical mass of people where once it gets past a certain point, it just grows so fast. So if nothing changes, things get really, really bad. So look at this constant right here. This constant right here is a constant that affects how fast things spread. Look at what, even if we just cut this constant in half. Look at that. Cut the constant in half. It's so much lower. Okay. And this is why it's important to take action. And I'm trying to not to turn this too much into a preaching video. It's more of a math video, the spread of the diseases. But again, please be safe. Please be careful. Just a small effort can go a long way, and a big effort could go an even longer way. All right. Because that is a very different, and it's just making the constant half. So things that we do really do matter for the spread of disease. All right, last example. We're going to talk about fish for a little bit. We'll end on a high note. Last example is going to be about fish. Example number 5. So a population of fish. Say they were introduced in a lake, maybe for fishing or something, if they didn't have natural fish there. Population of fish in a lake after T months is given by P of T equals 1,000 divided by 1 plus 19 e to the negative 0.1 t. So this is logistic growth model. All right. Specifically, the numerator is our carrying capacity. All right. So this mentions carrying capacity is 1,000 fish. So again, maybe the lake doesn't have enough food to sustain more than 1,000 fish. Maybe there's too many predators, like people fishing, that are going to be catching these people up. For whatever reason, this lake can really only handle 1,000 fish. Okay. So we'll have exponential growth, but eventually, due to other constraints, the exponential growth will start getting cut off. That's the whole idea about a logistic model. Okay, so part A is going to be graph T. So graphing this by hand, you don't really have to do, but you could do it. All right. But for purposes of the homework, I'm okay with you using a graphing utility. I'm not going to ask you to graph something by hand on a quiz or an exam. Okay. So we're going to look at this with Desmos. Population of fish. Y is going to equal 1,000 times 1 plus 19, e raised to the negative 0.1 times t. And you can see that we definitely have to change our scale. So t is in months. So let's look at a couple months. Maybe look at a year. And the carrying capacity is 1,000. All right. So this is growing really slowly. Let's not look at 12 months, 60 months or something like that. Okay, so this is 5 years that we're looking at right now. Okay, so notice, start with 50 fish, and eventually we get closer and closer to 1,000, but it slows down, right? When we start up, we have exponential growth. This first half looks like exponential growth. But then it really does kind of taper off, and we get really close to that carrying capacity of 1,000. Again, as we move to the farther to the right, it really gets very close to 1,000, right? That's what carrying capacity is all about. Okay, so that's kind of the graph. So part B, what is the initial population? Initial population, find it. I got the order of my words a little off. Oh, not even wearing my Yoda shirt, of which I have one. By the way, I do have a Yoda shirt, but it's green. Green shirts don't really work so well in my apartment. Okay, so initial population. You might think, well, it's not the 1,000. 1,000 is carrying capacity. Maybe it's 19, but it's not. Initial population, that's y-intercept. Okay, well, how do we find the y-intercept? We've been finding y-intercepts this whole semester. The y-intercept is just when x is equal to 0. Or in this case, when t is equal to 0. T is our variable here. So all we're going to do is plug in 0. If we plug in 0, we're going to get 1,000 divided by 1 plus 19 times e to the this times 0. You could do this by hand, or you could type into a calculator. Either one's fine. E to the 0 is 1. So type this into a calculator, you're going to get 1,000 divided by 20, which is 50, just like the graph said. So initially, 50 fish were introduced into this lake. And eventually, they're going to grow enough. As a side note, there are some really cool models that deal with what happens if too few fish were introduced. Then we're not going to grow to 1,000. We're actually going to have the fish die off. If there's if the rate of rate at which they're getting eaten or something is more than the rate at which they're reproducing, something like that. We're not going to talk about that in this class though. But as you change the parameters, the graph can go different places. That's called a bifurcation, which is pretty cool as well. Anyway, not in this class, but there's some cool stuff to talk about with math. Part C. What is the population after 6 months? So what was T? We need to know what T was, right? Population of fish in a lake after T months. Okay, so T is in months. So after 6 months, that's just P of 6. You just plug in P of 6, 1 plus 19, e to the negative 0.1 times 6. All you do is just plug it into a calculator and round to the nearest whole number because we're dealing with populations, okay? You definitely don't want fractional populations. That's weird stuff. So 1,000 divided by 1 plus 19, e raised to the negative 0.1 times 6 is going to be 87.5. That's going to round to 88 fish. So we started with 50 fish. After 6 months, they're not reproducing very fast. Okay, we have 88 fish. All right. That's why we had to zoom out in our graph, right? We zoomed out to 5 years to really see that full shape of the logistic growth model. All right. Part D. This one's the tricky one. When is the fish population? 900. So it's going to be a long time. It took 6 months to go from 50 to 88. It's going to take quite a bit to get to 900. But let's find out exactly when. Right, the fish population, that's when is P of T equal to 900. Population is 900. So we have to solve for the T. So that's what we're going to do. Excuse you, microphone. When is the population 900? That's when the left-hand side is 900 and the right-hand side is 1,000 divided by 1 plus 19 e to the negative 0.1 times t. And this is not trivial to solve. But remember, anytime you're solving an equation and you have a denominator, one of the best ways to solve it is to get rid of the denominator. Let's multiply both sides of the equation by the denominator. So 1 plus 19 e to the negative 0.1 t over here. And over here as well. 1 plus 19 e to the negative 0.1 t. So on the right-hand side, they cancel out. Left-hand side, we have to distribute. Distributing the left-hand side is 900 plus 19 times 900. I'm not going to do that in my head today. 19 times 900 is 17,100. E to the negative 0.1 t equals the right-hand side, which just canceled to become 1,000. And now we've got an exponential equation. So with that one step, as soon as we got rid of the fractions, by multiplying by the LCD, we just have an exponential equation. Isolate the exponential and then undo it. So subtract 900 from both sides. 1,000 minus 900 is 100. And then divide both sides by the coefficient, e to the negative 0.1t. Equals this divided by that. That'll be 1 over 171. You could use a calculator. Take the natural log of both sides to get negative 0.1t is equal to the natural log of 1 over 171. And divide both sides by negative 0.1. Well, the natural log of 171, or 1 divided by 171, excuse me, divided by negative 0.1. And that could be simplified a little bit, but we're just going to plug it into our calculator to see what t has to be. If you type that in, you get 51.4. That's how many months it's going to take to have 900 fish. So again, that's like 4 years. 4 years is 48 months, and then 3.4 months, approximately. And again, I would take this answer over here as well, 51.4 months. I'll take it here. So yeah, maybe if we wanted a robust fishing population, we should have introduced more fish into the lake. Okay. And again, as a reminder, this is what it's looking like. We're asking, okay, how long until there's 900 fish? That's the y value here. Y value is 900 right around here, which is, yeah, 51.4 months. All right, so it's verified by the graph. So those are the two big long sections. Okay, the next two sections are pretty quick. We already did all the hard stuff. Let me know if you have questions, and good luck.